is by using this rule. So recursively, I always have to tell you where to start, and then I have to tell you how to move. So if I want u sub 2, and remember n has to be positive integer, right? And I'm supposed to use the positive integer after 1, so I'm going to use 2, is equal to u to the 2 minus 1 plus 5. But what is u sub 2 minus 1? And then, of course, how do I get u sub 3? That's equal to u to the sub 3 minus 1 plus 5, which is u sub 2 plus 5, but u sub 2 was 8. And so on and so forth. The explicit definition means I'm going to give you a rule where I can jump to any term. It doesn't depend upon the term before it. So an explicit definition, and I'm just using k's this time, a sub k, and a's, a sub k is equal to, take the k, square it, and add 2 to it. Whoops, sorry. So for instance, let's say that I had, right, and no, I probably should have said what I want you to start k at. So let's say for k is greater than or equal to 1. So let's say a of 1 is equal to 1 squared plus 2. A sub 2 is equal to 2 squared plus 2. A sub 3 is equal to 3 squared plus 2, and so on and so forth. Good. Okay. So again, I could say to you, given this one, I could say, hey, what is a sub 10? You don't need me to go a sub 4, 5, 6, 7, and 8, and 9 before you give me a sub 10. That's the power of explicit. You can just say 10 squared plus 2. But with recursive, since you are always dependent upon the term before it, if I asked you to use the recursive rule to get me u sub 10, that'd be kind of annoying, right? So that's why it's kind of nice to be able to, given recursive, get to the explicit, especially if you need lots and lots of terms. Excuse me. So as I mentioned, there are two types of sequences that we are most interested in. The first one is arithmetic, and I made this number 1, but in the rankings for what we're going forward, actually it's geometric sequences going forward that are the most mathematically interesting to us. But arithmetic sequences are important. They are a type of sequence. They are asked about on SAT 2s. So an arithmetic sequence is first and foremost a sequence. So it's a list of terms, a list of values, a list of numbers, separated by commas, in which each term can be obtained by adding a common difference, and we call that common difference D, get it, for difference, to the previous term. So an arithmetic recursive definition looks like this, and that first example I gave you with u's was an arithmetic sequence, right? And so I just used it again here. I just copied it over here with u's instead of a's because, again, it doesn't matter. But a recursive arithmetic sequence means you're taking the term before it and adding the same value over and over and over again. So again, if I was exactly what I did before, if I tell you to start at 3, every successive term is generated by adding 5 to the previous one, right? And of course I'm going to start at greater than 1 because I already gave you 1. I could also do this. I could also write it like this. Because again, remember, Your domain is positive integers. What you are inputting is positive integers, and what you are getting out are values of the sequence. Values or terms of the sequence. Okay? Explicit, here's my explicit rule. My explicit rule is where did you start plus your common difference times the previous subscript, not the previous term. So look at what this looks like here for me, for my same rule up here. My first term, and again, you can use A's, whatever. My first term is a 3. My common difference was a 5. And this is the subscript before it. That's an explicit definition. So if I ask you to find the first 4 terms and the 8th term, notice I've color-coded these. For the 4th term, I think I'll probably just use my recursive, right? Because I've got, they want the list of the first 4 terms. Well, I've got u sub 1. U sub 2 is simply 3 plus my common difference. Right? Now I could easily keep going, but what if that was this was the 80th term? Right? Using explicit, if I just want to jump to the 8th term, a or u sub 8 is equal to the first plus 5 times, not the 7th value, but but how many came before it? 8 minus 1, aka 7. Now, I kind of gave a little hint before of domain and range. If we have a domain of positive integers and a range of values out of the values of the sequence or the terms, well then I can graph, can't I? The first term is 3. The second term is 8. The third term, hey. Now these are discrete values, but they all lie in a what? Discrete meaning I don't, right, my domain is only positive integers, so I'm not connecting these dots, but can you see the pattern? Wait a second. Look at this. Hello? What's the S word that we use for this in algebra land? Right? So what if I expand this out? Right? Remember, D is just going to be a number. Right? Number times, here's my independent variable. So a sub 1 is a number, and d times negative 1 is a number. Excuse me. So can't I write this as d, a number, times n, my independent variable, plus, oh my Lanta, that is a linear function. I mean, in discrete terms, right? Right? There's slope plus this is mx plus b, oh my Lanta. Let's see what that would be for us here. 3 plus 5n minus 5 means 5n minus 2, right? A sub n becomes 5n minus 2. What happens when you plug 8 into that? OMG. Now again, the y-intercept doesn't really have any meaning for us, right? Right, to add -2 because our domain is only positive, positive integers. Now if you get your calculator out, you can do, maybe you know this already, but on your home screen, if you just hit 3 plus my common difference, and then you do it one more time, if all you have to do now is just keep hitting enter. Snap. All right, that's pretty cool. All right, check. So let's do these. This is how some of your homework questions are phrased. They ask you to, given these series, find the common difference. So as soon as somebody asks me for a common difference, I know I'm dealing with an arithmetic sequence. Then they're asking me for the 10th term. Then they're asking me to write the recursive rule and write the explicit rule. So arithmetic means common difference. So I like to do this. -1 minus -7. Double check and make sure that another difference between subsequent terms are the same. So I've just answered part E. I'm sorry, part A. I'm actually going to skip B and I'm going to go to the recursive rule. The recursive rule is the next term, A sub n, is for arithmetic the previous term plus my D. Right? That's my recursive rule. Tell me where I start. Right? So if you started with 1, then you're going to start numbers, right? You're going to start with A sub 2, so A sub 2, oops, sorry, not 6, -7, my bad. So what is A sub 2? Double check to make sure. What is A sub 2? That would be -7 plus 6. Sure enough, that's -1. Check. Now I'm going to go and find the explicit rule. And remember, the explicit rule is A sub 1, which I see, plus my common difference times the previous subscript. Now I think I will go for the 10th term. Since I'm going to jump to the 10th term, I like to have the explicit rule. So what is this, 9? Right? 10 minus 1 is 9. 9 times 6 is 54. 54 minus 7 is 47. Make sure I did my math right there. Right? Anytime you're doing simple computations, I can certainly be off. Yay, I feel good about myself. I got it right. So just because they ask you these things in this order doesn't mean I have to go in this order. All right, so maybe you want to pause the video and see if you can do the next one. But if not, follow along with me. minus 26. Now, because they already told me that they were asking me for the common difference, well, I don't really have to check, right? But it's nice just to make sure that your math is right. What is 4 minus 15? What is negative 7 minus 4? They need to all be negative 11. They are, and I can call that my D, and I've just answered part A. Remember, I like to skip part B and go right to part C. Part C, recursively, the term before it, minus 11, given that your first term was 26. My explicit rule is that first term, minus my common difference times the previous subscript. So now I can go and answer B. A sub 10 so 26 minus 11 times 9, and I got negative 73. And again, picture what this graph looks like. So this graph starts this time up here at 26 and decreases every time by 11, right? Again, a linear pattern. Arithmetic sequences are linear in pattern, either with a positive slope or a negative slope. What the hee-haw's going on here? Why did logs have to come into the situation, right? Note, don't let ugly things, don't be judging, right? This is all base 10. What is my common difference? Log 6 minus log 2. That's not log 4, right? Do you remember your rules? See the log twice with subtraction in between, write the log once, and divide. Right? 18 divided by 6. Guess what 15 divided by 18 is? Right? That's using the logs of the rules of logs. Yes, you have to know your log rules. They don't go away. So what is my common difference? And I've just answered part A. So again, I like to skip part B, and I go to C. My recursive relationship, let's use this time. U sub n is the previous term plus D. What is my explicit rule? The first term, first term plus my slope, Log 3 is just a number, the exponent that turns 10 into 3, times the previous subscript. Whoa. Now remember, B is asking me for the 10th term. Right? Now, do you remember some of your properties here? Right? Let's get an actual, what would, if I'm doing a multiple choice and that answer ain't there? Oh, my pen went a little nuts there. Sorry. Log 2 plus log 3 to the 9th. See the log twice with addition in between. Write the log once and multiply. That answer was the multiple choice answer. Oh, snap. Now, let's go back to the calculator. Right? Because what if I told you, right? I told you before how you could get your calculator to do this. So what if we had log 2, right, was our first term, and to get the next term we had to add log 3. And then what if I just add log 3? Right? So this is the first term. This is the second term, this is the third, fourth, fifth, sixth, 7, 8, 9, 10. Now remember the expression that we got. Let's check our work. Remember the expression that we had was log 2 plus nine times log 3. My Lanta. Or log 2 times 3 to the 9th. Math is beautiful. Aight, let's go on. Geometric sequences. Again, for certainly next year, geometric sequences and then geometric series are what we work with the most. It's also a sequence, so a geometric sequence is a list of terms separated by a comma, but instead of adding, geometric sequences are generated by multiplying a common ratio. Just means you have a fraction. So the recursive rule, how you get any a sub n after a sub 1, is you multiply the common ratio times the previous term. So this is an example. If, for example, I tell you that my first term is 4, and how you get every other term is multiplying. Now this is a fraction, right? It's 2 over 1. You multiply each term by 2. So the first term is 4, the second term is 8, the third term is 16, and so on and so forth. The explicit rule, how you explicitly just jump to a term, is you multiply the first term times your ratio and the subscript before it. So using my previous example, if I told you here's a sub 1 is 4, here is the common ratio, and this is the subscript. So if, let's say, I wanted the 10th term, whoops. And remember, you don't order of operations matters, right? You do the exponentiation first before you do the multiplication. So 2 to the 9th is what? 128 times 2, is that right? No, that's 2 to the 7th, 2 to the 8th, 2 to the 9th, 5, 12 times 4. So let's do some examples of that. If I want you to find the first 4 terms and the 8th term, again, the first 4 terms, I had those, right? I kind of like did this already, right? Just multiply by 2. I don't know why I erased all this. And then the 8th term, which is really, funnily enough, right? Isn't that 2 to the 9th? Because this is 2 squared times 2 to the 7th. Now, the same thing will hold with your calculator here. You can say, oh, my first term was what? I forget already. My first term was 4 multiplied by 2, and I get 8 times 2, and I get 16, and then I can just keep hitting enter and get all the terms that I like. Okay. So these homework problems find the common ratio, the 10th term, the recursive rule, and the explicit rule. And again, common ratio means I'm dealing with a geometric sequence. So this time, instead of subtracting 6 and 3, I find a common ratio. Right, and you can see that for each one of these, my common ratio is 2. So I just answered A. Just like before, I'm going to skip B, and I'm going to go to C. The recursive rule is multiply your common ratio times the term before it. The explicit rule is your initial, right, a sub 1, or u sub 1 in this case, times my common ratio to the previous subscript. So now I will go get the 10th term. And I'll let you multiply that out. How about the next one? What is that? And is it the same ratio as? And is it the same ratio as? And is it the same ratio as? Yes, it is. And that common ratio is not 2, but -2. So I've just answered A. C. D first term times common ratio hey, wait a second. What if I was asked to do this on a multiple choice and this answer wasn't there, the explicit rule wasn't there? I took Algebra 1 and I paid attention. Isn't this the same as -2 to the -1? And isn't this -2 to the n-1, which means see the same base twice with multiplication in between, write the base once, and add, baby. Oh, snap. Now I'm going to go ahead and do the 10th term. And I can use either version, right? Now before I do the third one, remember how with arithmetic I kind of talked about the relationship between an arithmetic sequence and a linear pattern? What's going on here? My domain is still positive integers, right? But what's my range? This is not linear, right? The rate of change is not constant. What is this? If you were to connect it, what would it be? Swoosh! Remember, an exponential function with a base that's greater than 1 is a swoosh. Now it's a discrete swoosh because my domain is only integers, but it's a swoosh nevertheless. Do you remember the issue with why we said for exponential functions we couldn't have a negative base? Do you remember? Because what does this look like? I still have my domain of positive integers, but I have a range of -1/2, 1, -2, 4, -8. Remember, this was my Super Bowl situation. I mean, that's fine. It's fine, it exists. It's just when we were dealing in function land in AAF, the analysis and application of functions, we couldn't have this scenario. So we said we don't, in function land, exponential function land, we said your base cannot be negative. And your base cannot be 1 because then you just have a constant function. But here in sequence land, this is just fine, right? So before I even talk about this one, and answer the questions, can you talk to me about the graphical pattern? Domain, integers. Range, first term, 48. Second term, 24. Third term, 12. Fourth term, 6. What is this? This is not a swoosh, it's a slide, baby, slide. Right? What is my common ratio? What do you think? Can you predict what your common ratio would be? My common ratio is not 2, it's 1/2. Oh, snap. So that's R, which is the answer to A, the common ratio. Skip to part C. My recursive relationship is just my common ratio times the term before it. So 48 times 1/2 is 24. 24 times 1/2 is 12. 12 times 1/2 is 6. 6 times 1/2 is 3. 3 times 1/2 is 3/2, and so on and so forth. How about the explicit relationship? That's the 48 is my a sub 1, my initial condition, times my common ratio, which is a number between 0 and 1. OMG, this is an exponential discrete graph that slides off to 0. As a matter of fact, what is the limit as n goes to infinity of this sequence? Oh my Lanta. What is that limit? Can you tell? Hello, horizontal asymptote? What is this limit? Of this sequence? Boop, 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 boop. It's like a Pong situation, right? There is no, right? Nope, can't answer that question. I can answer this one though. What is the limit of this sequence as n goes to infinity? It's not a number though. What is the limit? Positive infinity. Oh, Ms. Gratz, I see what you did there with the warm-up. Right? There's some link between our limit discussion that we did, started it in AAF, right? And with functions, and we continue it in IB Pre-Cal when we were dealing with functions, and then within the subset of rational functions. So I'm taking that same kind of thinking now and applying it to sequences. All right, what's happening here? I was just starting to get excited about limit work. The second and the fifth term of a sequence. All right, so this is a sub 2, and this is a sub 5. Find the explicit and recursive formulas if this sequence is arithmetic. What am I going to do with that? Well, whoops, sorry. Hit the wrong. Arithmetic. If I have an arithmetic sequence, then I have a common difference. But I don't have sequential terms, so I can't find it, right? Just by subtracting 24 and 3. Well, well, wait a second. Isn't it true that whatever a sub 2 is, which by the way is 3, didn't I get that by saying that's a sub 1 minus what? I'm sorry, plus, right? What's my recursive formula? A sub 1 plus my common difference times the previous subscript. So could you see why I used this? I don't know what my D is, but I found an equation that I can't fill in a sub 1, but I can fill in 3. And this is D times what? 2 minus 1. Oh, snap. So 3 is equal to a sub 1 plus that common difference. What about a sub 5? Can I do the same thing there? A sub 5 is equal to a sub 1 plus that common difference times 5 minus 1. So that's 24 Look at that. Gee, can't I just subtract those two functions? And 24 minus 3 is 21. A1 minus A1 goes away. And 4D minus D is 3D. So what is my common difference? Oh, snap. So if my common difference is 7, they want me to find the explicit and recursive formulas. Well, a sub n is equal to the first term, a sub 1, plus 7 times n minus 1. And my recursive formula is a sub n minus 1 plus d. So the only thing I'm missing here is this a sub 1. How do I get a sub 1? Oh, right. Here, right? I found d and I had this system of two equations. So isn't it true that 3 is equal to a sub 1 plus 7, meaning a sub 1 must have been negative 4. Well. How do I handle that if these were geometric? If these were terms for geometric, I'm going to use the same kind of thinking, right? A sub 5, which is 24, is equal to a sub 1 times r to the 5 minus 1. And a sub 2 is equal to a sub 1 r to the 2 minus 1. So 3 is equal to a sub 1 r to the first. I don't have this nice like add down situation though, do I? What do you think I can do? Hey, if I do put this over here, I had two equations up here and I subtracted. Well, I have two equations here. What if I just divide them? 24 divided by 3 is 8. A1 divided by A1 is 1. R to the fourth divided by R to the first is R cubed. Therefore, R must be two. And if R is equal to 2, what is A? 3 is equal to A1 times 2. So A1 must be 3/2. So now I can write my recursive R times the previous relationship and my explicit one would be a sub 1 and just to show off, and I would only do this to match a multiple choice answer. I'm going to do the same thing I did before. right? You can absolutely stop here. You can absolutely stop here, actually, right, for our problems. I just wanted to show you this for that SAT-2 problem that aren't the answer to all of them, but is sometimes the separators between the perfect and the not perfect, right? It is really the mathy kid that gets that multiple choice right. Right? Doesn't mean you won't get a good score if you don't recognize that. All right. Here it is again. Limits. So, limits of infinite sequences. Sequences, remember, are a list of terms, and if it's infinite, it's going to go off forever, right? So I want to introduce some new language to you. Converge and diverge, and that's really hard sometimes for kids to conceptualize what we mean by converge. And I've given you the fancy little definition here. But the limit of an infinite sequence is said to converge if the limit as you go off to infinity of the terms is a number, not an infinity. That's what it means for some finite L. Just means the limit has to be a number. It can't be does not exist, and it can't be infinity, and it can't be negative infinity. So if the limit is positive or negative infinity, or the limit does not exist, then we say the sequence diverges. So let me do the first example, and then I'm going to show you some of what happens in my head when I think converge and diverge. So look at this sequence. -1 to 1 to -1 to 1 to -1. Here's the pattern, right? Remember, your domain is positive integers, so you have -1 to the first, -1 squared. This is a very boring sequence. But think about the graph of that, right? When you think about the graph of that, -1, 1, -1, 1, -1, 1, -1, 1. As you go off to infinity, is there a pattern, right? And a pattern that you could describe like you describe a horizontal asymptote, right? Are all the terms approaching a value? And I hope you can see that there is no pattern, I mean, other than Pong, but we call that limit, right? We say the limit as the number of terms goes to infinity of those terms does not exist. Therefore, this sequence diverges. Let me actually do another one. Here is a sequence, 2, 4 of all the even integers. Think about what that looks like graphically with a domain of positive integers, 2, 4, 6, 8, 10, 12. I hope you can see that this actually does have a linear pattern, doesn't it? This is a linear pattern. Again, it's not connected. But what are those terms approaching as n approaches infinity? The limit of the terms of this sequence, right, which would be 2n, right? Exists, but it's infinity. Therefore, we say that this sequence diverges. Next one. Think about what's happening here. I don't know why that happens. 48, 24, 12, 6, 3, 3/2, 3/4, 3/8, 3. What's happening here? Right? What's happening here? What is the limit as the number of terms goes to infinity of this sequence? What was the pattern? This was a slide of those terms, right? And where were they sliding? Therefore, we say this sequence converges. So it all depends upon the end behavior. So let me show you how I kind of think of these. And if this messes with your head, this just happens in my head. So if it doesn't happen in your head, don't let these visuals mess with you. But when I think converge, I think of like dominoes or bricks or going over and over and over again. And this one was bricks. Look. I don't know why this volume is what it is, but, or I mean, right? Do you see that? Just, I think, that's what I think is converge. Converge is collapsing, right? All the values are collapsing. Woot! Or, conversely, when I think diverge, this is what I think. Diverge is going off, right? Going off into space, going off into the air, right?
When I first saw this product, I thought it looked kind of crazy.
I don't think about this product
Didn't really understand
at all.
what the benefits would be, but I had seen some.
But I think, oh, those terms are growing, 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 and off they go, swoosh, into the air. Swoosh. You ain't converging, baby. That's a divergent issue, right? Divergent. Whoosh, off you go. Yes, I know, I'm very weird. So, how about this one? How about this one? Right? What's happening here? Can you see what's happening with these ones? Right? What's happening to these terms? I started really with 1/1, then 1/2, then 1/3, then 1/4. What does the graph of 1/n look like as you go off to infinity? Asking if you converge or diverge is asking you for the limit of those terms. So as the terms go to infinity, what is the limit of that sequence that is represented actually in this form by 1/n? Since the limit is a number L, it is a number, therefore we say the sequence does what? Remember, this was, the limit does not exist because I bounced. This one went off in a linear pattern. This one went off in an exponential pattern, right? But it's really dots, right? I should have drawn dots. This one, exponential decay. How about this one? What is going on here? What's going on here? Right, I've got 1, 3, 4, 5. This is kind of crazy. I wonder, this is harder to picture what's going on. Maybe I should keep going, right? 6/5. Then this is going to be 7/6. then this is going to be 8 over 7. Gee, as I go off to infinity, right, aren't I always going to have a ratio where the numerator and denominator are only off by what? Right, in each one of these successive terms, the numerator and denominator are only apart by 1. Those values, so what do you think is going to happen when you get way out here and you have a numerator and a denominator? So I have 1 gazillion, 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 and then the denominator is either just 1 or bigger or just 1 smaller, right? Either plus 1, the numerator plus 1 or the numerator minus 1. What is that limit approaching? Yeah, that limit is approaching 1, which is a number. Therefore, this sequence does what? Converges. So number 5 are ones that cause the most trouble for kids and thinking about what they're doing, because I wasn't sure. What did I like about this? I liked about both of these that somebody gave me a rule and I could kind of like plot then a bunch of values in my head. I could think about what those values were doing. This also, a nice arithmetic sequence, a nice geometric sequence, and I could tell that that geometric sequence was going to swoosh off to infinity. So I like ones because of my prior knowledge and prior classes and graphical knowledge. I can kind of fit those sequences into a known pattern right away. It takes me a little bit more time with these sequences that are kind of outside of the norm. So, but again, remember I told you when we first started that the sequences that are most interesting to us are your arithmetic sequences, right? We spent a lot of time defining explicit, recursive, and the rules, and then geometric. So these are the sequences that we're going to be dealing with the vast amount of time, and then every once in a while I get an outlier. Maybe it's arithmetic, maybe it's geometric, but I don't recognize it right away. But more often than not, you're going to be dealing with arithmetic. So let's see if we can make some generalizations here about if we know we're dealing with an arithmetic sequence. Don't you know, haven't we talked about graphically, arithmetic sequences are either, we figure out geometric has that common ratio, and we figured out that was an exponential pattern where when the common ratio was greater than 1, we had our swoosh. When my common ratio was between 0 and 1, we had our slide, and when our common ratio was negative, we had our Pong situation. So the limit does not exist when we've got Pong. The limit is infinite when the common ratio represents a swoosh. But when the common ratio is between 0 and 1, we have our slide, which means our limit is 0. So the only geometric sequences that converge are the geometric sequences where R is between 0 and 1. Oh snap. Good patterns. So I'm going to put the warm-up. Now again, what if we don't have, what about some non-arithmetic or geometric? Remember, this one was not arithmetic or geometric. Well, I guess you could kind of sort of think about it as geometric, huh? Where my r is -1. Anyway, my point being that if somebody gives me a rule, it's better than this, where I have to kind of think of a rule on my own. So I want to put the warm-up back. Oh no, first I wanted to do this, sorry. I already did this, I already did this, I already did this, I already did this. This is what I wanted to talk about. Right, we talked about this is, right, 1 over n. This one we took a little bit more trouble to figure out. This was arithmetic. This was Pong. It was geometric where r was -1. This is none of those. But this is why I want you to remember the warm-up. Think about this as, remember, asking if it converges or diverges is asking you about the limit of this sequence. Five halves.